the field line representation is actually deceptively powerful. Even though it's very intuitive, underlying it has extreme mathematical rigor, which allows us to make some very powerful mathematical statements. And I want to show you one of the first examples of that, and that has to do with the actual meaning of the density of the field lines that we see. You see how they're concentrated here near the charge, and then they're a little wider apart in between the charges. There's a very precise mathematical consequence related to the density of field lines, and I'd like to discuss that with you now. And we can pull out, actually, this deeper meaning, again, by thinking very carefully through our rigorous analogy to the fluid flow. So I'd like you to imagine the following situation. In this situation, I'm going to have a stream, right? I'll have a stream here, so the little bit wavy on top to represent the fact that it's a liquid. And I'm going to have my liquid flowing across through this stream from left to right. But what's going to make things a little different, a little more interesting here, is that the stream bed, which I'll sketch for you down here, I'll kind of fill that in, that's the stream bed. As I move across, the stream bed is actually going to move upwards, and the stream is going to get more shallow as I move along. And the question then relates to, well, what happens to the flow of the fluid? I have these streamlines, and as you can imagine, the streamline near the surface pretty much just continues going straight through, but the streamline that goes near the bottom of the stream has to eventually get squeezed up and come through out on the other side, and there's going to be, of course, all of these other intermediate streamlines that have to accommodate as the stream bed gets narrower and the region for flow becomes smaller. And the question then is going to be, well, what will happen in a situation like this? What happens to the velocity of the fluid? Now, if you've ever been, whitewater rafting or have any experience with a stream, you actually know what happens when the field line, or I should say the streamlines like this, are squeezed together. If you've ever been in this situation, and here I'll show you a picture of it, what happens to the stream, this is the deeper region over here. Let's see, get my mouse here. You have the deeper region, and then over here is the shallower region. And you can see what happens. You have this deep, peaceful water. Then as it becomes shallower, all of a sudden you see like these ripples on the surface. That's because the water now is starting to move much more rapidly through that shallow region. That's why the rapids are where the river is more shallow. So we know from a fluid situation that as the bed becomes shallower, what indeed is going to happen is that the velocity is going to be faster. And it would seem then that there's a correlation between how dense these field lines are, or streamlines are, and the velocity of the fluid. But because we have exact correspondence between electric field lines and streamlines, that will tell us also that there's some mathematical rule relating the concentration of electric field lines to the actual strength of the electric field. So let's see if we can make this a little bit more rigorous. Let's see if we can kind of really derive this. So what I'd like you to do is to consider those original two field lines that I had sketched for you, the one near the top here and the one near the bottom. And I want you to imagine that what I'm going to do is I'm going to take all of the fluid between those two streamlines. I'm going to take some little area element of the fluid, and I'm going to trace out a funny looking shape. It's going to be kind of like a pipe shape, like so, but a curved pipe. And the mouth of the pipe will be over here, like so. And I've chosen the surface of this pipe to move along directly with a field line. That determines the outline of the shape. And that's important because then the total number of field lines entering into my shape will be the same as the total number of field lines exiting. Also, when I do this, I know no flow of fluid is going to be crossing outside of my surface. And that's where I can start to become mathematical. Because fluid isn't leaking outward through this funny shaped surface that I've picked, I know then that the total current which flows in, I in, that's going in, the total current in has to match the total current out. And I can use that conservation of mass then as a basic principle in order to make a mathematical statement about the velocity. Now, we know how to relate current to velocity. That is our integral of the flux. We can write that as integral, recall, over either surface of the flux, which is equal to rho naught times the velocity. In other words, the current density, J, and that's the current per unit area. And then, of course, we have to dot that with the area element, dA. Now, to carry out that integral, I need to know something about the fluid. So I'm going to think on this surface, there's going to be a velocity, which I will call V1, and I will call that area that of the stream that's entering into this pipe shape that I've defined, area A1. Over here now things are squeezed down. They are traveling at velocity V2, and my job is to determine this velocity. But the field lines have all been squeezed down, or streamlines, into a much smaller area, which I will call A2. Now, if we look at these integrals, I'm going to equate the result on either side of my bottle shape. And so I will be evaluating this integral twice, once for the left side and once for the right side. Let's go through that evaluation. Now I'm taking an incompressible fluid. That means that the density, rho naught, is constant. I can pull that out of my integral. I'm also going to imagine that I've taken a small enough shape so that the velocity is essentially constant across my shape. The shape I've drawn here isn't that isn't that small in comparison to the stream, but you can do this on a rigorous basis. And then what I'm left with is that velocity dot dA, and as we know, that will become the magnitude of my velocity times the magnitude of dA times the cosine of the angle between them. But I've chosen my bottled shaped surface to have these surfaces perpendicular to the velocity field, so that angle theta is going to be 0, and the cosine is going to give me then a 1. So I'm left with rho naught. In fact, I'm going to move this a little lower. I'm left with then rho naught factors out. The velocity on either side can factor out. So rho naught times the corresponding velocity times the integral dA, because after all, the magnitude of the dA vector is just dA. The velocity will be either the velocity on the left or the velocity on the right. This integral dA then just gives me the area. So in either case, I'm looking at the density times the velocity times the area, and that has to be the same whether I'm on the left or if I'm on the right. So the final mathematical statement I'm going to make then is that the incoming current is rho naught times the velocity on the left times the area on the left, and that has to equal the outgoing current, which is the density times the velocity on the right times the area on the right. And then I can look at this equation and I see that what's happening is that the velocities are inversely proportional to the areas. I'm finding that the V1A1 equals V2A2, and it's directly constant as I go from the beginning of the flow to the end of the flow. So I could solve, for example, for V1. It's going to be whatever my constant is divided by A1, and likewise V2 will be whatever my constant is divided by A2. So I see that the velocity is actually proportional to 1 over the area. Now, that is what is true in water world, but as we have seen, we can set up a direct analogy between our streamlines and the electric field lines. So the same statement can be made for the electric field. The direct analogy to the magnitude of the velocity, of course, then, is the magnitude of the electric field. So the magnitude of the electric field is going to be inversely proportional to this area. So it's going to go like something divided by area. And one thing that we can track, as I had commented, one thing that is constant from one side of my bottle shape to the other side of my bottle shape is actually the number of field lines. So that will be constant, so I can refer to the, I can make the numerator the reference point, the number of field lines, per unit area. And that then can be rigorously tied to the strength then of the electric field. With this in place then, I'd like to summarize everything that we've been learning about the electric field and the electric field lines, and also draw some more lessons about them. It turns out that whereas we can usually intuitively reason directly from our fluid analogy, sometimes things get a little bit tricky. So it's nice to have a well-defined, rigorous set of rules that we can make sure that our diagrams obey to help ensure that we do have accurate portrayals of how the electric field behaves. So these are the lessons you want to keep in mind when you make any sketch. The first thing, as we just said, is that the magnitude of the electric field at any particular location is going to be proportional to the number of field lines per unit area. The second lesson that I would like you to draw is that the field lines, they can't just stop and end, right? Field lines represent the paths of tracer particles. So just as we saw in our dipole example, these field lines, they always begin, notice, where they are ejected into our system, right? They get pumped in down some hose somewhere, right? But they are always coming out at some positive charge. And they can't just then disappear from the system because mass is conserved. The only places they can get sucked out are at these special devices we introduce, these sinks where we are actually pumping fluid out of the system. So field lines also, you want to keep in mind that they always begin, or by parallel construction they end, they begin at sources which in the electric case are either positive or by parallel construction then negative charges. The third lesson, and this is what I really had just been saying, if we ever see a tracer particle suddenly appearing or disappearing, that means there must have been a charge there. When we are in an empty space, the field lines can't just begin or end. So field lines never begin or end except at charges. So if you do see a field line in a diagram beginning or ending, you know there is a charge at the edge of that field line. And you can determine whether it's positive or negative by referring yourself to rule number 2. Finally, a close consequence to this fact that the number of field lines per unit area is proportional to the strength of the electric field. The other factor that comes in is that because the strength of each source is related to how much fluid that it's pulling in, we also know that the number of lines in any diagram that enter or leave, enter or exit a charge is always in our diagram, should always be drawn as proportional to the actual charge Q. And if you obey these particular rules, you will always draw very accurate field line diagrams, provided you obey this last, sometimes subtle rule. Usually this one doesn't get into trouble, but there are some complicated cases where keeping this in mind is going to help you. As we'll describe in a moment, or we'll reason through in a moment, field lines they can never, this is very important, cross. They can never cross through each other. You can't have a situation where one field line is going like this and another field line is going like that. That's just not allowed. That's just not at all possible. So let me just indicate that with a classic slash through it. That cannot happen. Now, the reason why it can happen should be apparent when you think about what this would mean, right? There's something very suspicious about this idea, particularly if you think in the fluid analogy. How could I have tracer particles, right, that are passing right through each other? How can the fluid actually pass through itself? It can't, because it has it's an incompressible fluid. The density is always constant. You can't have particles that just pass through each other. Matter doesn't work that way. If you want to get to be a little bit more mathematical, notice that the tangent line, recall that the tangent to each of these lines has to always be proportional to the or in the same direction as the electric field. Well, the tangent to this line points in the direction of the arrow, right? And the tangent at this point to the other line points this way. Well, the electric field can't be pointing in two different directions at the same time, right? The flow has to only be in one direction at each point in space, and that thereby rules out any field line crossings. You'll see as you practice in your various assignments that sometimes when you get a diagram cramped together with lots of positive charges or something, you might be tempted to make this happen. But if you avoid this happening, you will end up with very nice and accurate field line diagrams, accurate enough that by looking at the concentrations of field lines, for example, you will be able to pick off how the magnitude of your electric field must be behaving.